I am actually quite fortuitous for the previous talk, introducing a lot of the things I'm actually going to be talking about today. And so first, hello everyone, my name is Schuyler Rosefield, and today I'll be talking about threshold symmetric crypto systems with low overhead. This is a joint work with Avi Schlott and Lakai Tyner, and you can find our paper on ePrint. To give a quick overview of my talk, I will first define what I mean by a threshold crypto system, and then I'll give some background on multi-party garbling, followed by our protocol and a few concluding remarks. Now, specifically within the context of this talk, I will be considering a subset of MPC protocols that instantiate threshold crypto systems. The goal of a threshold crypto system is to be able to replace a single-party crypto system, such as an RSA encryption and signature scheme, with a multi-party variant. A threshold crypto system consists of two parts, key sharing and evaluation using that key. We want to split up the key amongst all parties, such that no one person knows the key, and further, no set of parties less than size t can learn anything about the key. Concretely, I want to say that a set of parties that each have a share of the key can come together and compute functions using that key, and that we're guaranteed that each time the same key is going to be used, the key is not going to be revealed, and that our desired function is computed correctly. Abstractly, we're going to define the threshold functionality as follows that consists of two steps, setup and evaluation. During setup, all parties get together to sample the initial key used for the crypto system. They may also perform some additional computation to derive shared material from that key. In the case of AES, this could be the key schedule or other reusable values depending on your application. During evaluation, appropriately sized subsets of parties can use the shared key as input to a new circuit. This circuit could be used to encrypt a message or compute a MAC if you're using AES or SHA, respectively. Lastly, we want to prevent a malicious party from using the wrong key share or otherwise cheating in the protocol. If an adversary can influence the key, they may be able to learn more information about the related. They may be able to learn more information using related key attacks, or in signature schemes, potentially outright break it entirely. This is important because otherwise we might be unable to check the correctness of the output of our MPC without having access to the key. Our simulation model is that of standard simulation security, and that has been introduced here multiple times already. Roughly, we want to say that our multi-party protocol is going to be indistinguishable from the world that has a magic box with the key hard-coded and the parties have no knowledge of that key. The security we wish to obtain is with respect to a dishonest majority, a malicious adversary, and with UC security. Now, we do have efficient threshold schemes for a number of primitives, such as RSA, ECDSA, and BLS. There is a long line of research starting in the 90s with far more citations than I can fit on this slide. In these cases, a bespoke protocol is created that is more efficient than a generic scheme. Because each of these crypto systems has a nice algebraic structure, it allows and helps protocol designers to move more computation outside the MPC, leading to greater overall efficiency. The natural question then, of course, is how do we construct a threshold scheme for this symmetric case? And so at the beginning of the talk, I promised a scheme for symmetric crypto systems. And by this, I mean standard schemes such as AES or SHA that do not imply public key cryptography and are frequently used in, quote, the real world. Of course, I need to mention why this is not currently solved already. And as with many things in MPC, this is ultimately a question of efficiency. Each of these primitives does not have a very good algebraic representation beyond that in the field of two elements, as they largely consist of bitwise operations and permutations. For our case of maliciously secure dishonest majority threshold schemes, we only have the folklore scheme for these crypto systems, which I will define in the following slides. Briefly, I want to introduce some notation for secret shares that I will use for the rest of the talk. Here, I will be using single brackets to represent standard arithmetic secret shares and double brackets to represent a polynomial secret share. These have all the properties that you would expect them to have. I will also denote with a superscript the ith party's share of the secret shares. Now, I want to define the folklore threshold crypto system that makes black box use of a generic FMPC implementation. In this case, we're going to be using a speeds-like authenticated secret sharing scheme where all parties are going to hold threshold shares of a key, threshold shares of a global key alpha, and threshold shares of a MAC on that key. Note that the MAC is a multiplication of the value and the global MAC key. We compile the authenticated secret sharing operations, such as the input, verification, and reconstruction, into Boolean circuits that will be executed within FMPC. In this example, I'm showing the evaluation step of fthresh, where we have already generated our secret shares of the key. The circuit that we're going to evaluate going to execute at evaluation time must first check that the max on each of the shares is valid, afterwards reconstruct the shared values, and then finally compute the desired function using the key and any auxiliary inputs. One problem, though, is that for many of our desired applications, the cost of these authenticated secret sharing operations outweighs the cost of the actual function we want to compute. And so this is what I'm going to refer to as the overhead of the folklore scheme. That is, the cost to compute things besides our desired application. This is because checking the max within FMPC involves field multiplications, and the circuit for a field multiplication in F2 to the 128 takes an order of 1,000 AND gates each. In comparison, the circuit for an AES block encryption is only 6,400 gates itself. Our goal in this work is to remove this overhead by removing the need to perform these secret sharing operations within FMPC. We do this by designing a scheme that we call threshold authenticated bits that I will describe later in the talk. Parametrically, we can describe the cost of the folklore scheme in terms of the size of the circuit that we compile. Here, I'm going to be using I, G, and O to denote the number of input wires, AND gates, and output wires of a circuit. As you can see, the folklore circuits have a blow-up of at least N, being the number of parties, in number of inputs and outputs, and the AND gates depends on the multiplicative complexity in the field. We benchmarked a couple of examples, namely HMAC SHA-256, AES 128, and KMAC 128. We give the size of these circuits split into a key-only preprocessing phase and an online evaluation size. And we show that the size of the corresponding folklore circuit and AND gates using the speed style scheme I described before. In the AES example, we compute the full key schedule that results in 1,408 bits to be secret shared. And the folklore scheme that authenticates these values costs nearly 40,000 AND gates. With one quick graph, you can see how the folklore scheme scales with number of parties for the AES use case mentioned before. The green line indicates the baseline cost of evaluating the full AES circuit without any preprocessing or without any threshold secret sharing. The solid line reflects the total cost, the dotted line the cost of evaluation time with preprocessing, and the dashed line the cost to generate said preprocessing. Clearly, the folklore scheme has a significant overhead over the baseline scheme. Our main contribution is a threshold scheme for Boolean circuits that is without this overhead. Our core idea is introducing a new authenticated secret sharing scheme that we call threshold authenticated bits. Using these threshold authenticated bits, we completely eliminate the overhead during evaluation and significantly reduce it during setup. As you can see, the setup overhead is simply the cost of generating the O, threshold authenticated bits, and an additional O input wires to the circuit in FMPC. Evaluation is exactly the same cost as the baseline MPC cost. Hopefully now I've convinced you that there is a problem here to solve, and I'll be giving you some brief background on multi-party garbling, as it differs a bit from two-party garbling. To introduce some common techniques and notation, I want to talk about information theoretic max, authenticated bits, and vector OLE. To begin with, IT max, or information theoretic max, these are linear equations of the form m equals k plus x times delta. I will refer to m as the MAC, k as the instance key, x as the authenticated value, and delta as the global key. An adversary that attempts to forge a MAC m prime for a new value x prime has the same success probability as guessing the global key delta. Using information theoretic max, we build a Bedoza-style authenticated secret sharing scheme for a value. In our case, these values are going to be bits, and so we call this an authenticated bit. Here, each party holds an additive share of a bit x and a global key delta I. Every party is going to authenticate each other party's share using their global key using the information theoretic max. As each party authenticates every other party's share, when opening a value, all parties can verify their respective MACs to ensure all computation was done correctly. Some useful properties of authenticated bits include the fact that it is linearly homomorphic. That is, additions and constant multiplications can be calculated locally without any communication. Partly because of this homomorphism, we can prove relations about the authenticated bits that directly reduce to the soundness of the MAC scheme. The astute among us will notice that this information theoretic MAC correlation is exactly that as subfield vector OLE, for which we have protocols to efficiently generate correlations. Relatedly, there has been a lot of work recently on creating designated verifier zero-knowledge protocols based upon full correlations, and I know that I have many of the authors of these works in the room today, so I hope I chose an appropriate selection of these schemes. With authenticated bits out of the way, I can finally talk about authenticated garbling itself. This technique for maliciously secure garbled circuits was first proposed by Wang et al. In the two-party setting, and then expanded to the multi-party setting in the same year, with many follow-ups in both the two and multi-party cases. Like standard semi-honest garbled circuits, authenticated garbling is the state of the art for maliciously secure Boolean circuit FMPC, with some caveats if you go to way too many parties. Also, like other garbling schemes, these are still constant round protocols and are largely network bottlenecked, as the local computation consists primarily of cheap PRF evaluations. At a very high level, authenticated garbling works in the following way. All parties are going to be jointly computing the garbled circuit because we cannot rely on any one party to be honest. This is first done by sampling authenticated permute bits for each gate and input wire in the circuit. When garbling, we're going to be defining an authenticated bit for each wire in the circuit and generate labels such that the evaluator can calculate either a share of 0 or an authenticated share of 1. After evaluating, because we have authenticated bits for each wire, we can run a check to ensure that every gate was calculated correctly. An implied and very useful property for us is that all of these schemes have the ability to take an authenticated value as input to the computation. Great. So in fact, we're going... All right, so... Does someone have like an oboe to like fight them off with? Is it coming from inside the lecture hall? Maybe. All right. All right, so in fact, we're going to rely on the capability of these garbling schemes to take as input an authenticated bit. That is, in addition to other inputs, parties can sorry. In addition to other inputs, parties can submit their authenticated bits that is treated as a single input by FMPC, regardless of the number of parties. Now I'm going to go into some more technical details of our protocol. The core notion of our protocols is a new concept called threshold authenticated bits, and whereas an authenticated bit is an additive secret sharing of a value, a threshold authenticated bit, which I'm going to indicate with double angle brackets, is a polynomial secret sharing scheme. Here I'm going to be using double brackets to signify specifically a T of n Shamir share of a value in f2 to the k. Our first observation is that Lagrange interpolation, or the process of opening a Shamir share, is a linear function. This means that we can apply this function to authenticated bits without any communication. Then, if we have authenticated bit representations of Shamir share values, we can interpolate to create an authenticated bit representation of that value itself. The important question is then, how do we generate said threshold authenticated bits? This is done in 3 steps, and at the end we need to verify that we actually have a sharing of an appropriate degree t-1 polynomial. The first step is simply creating candidate Shamir shares, where we sample a random secret share, and each party receives the evaluation of the polynomial on a fixed point as their share. This is just a standard semi-honest broadcast, and we don't verify that we have received a valid sharing yet. The second step is authenticated to secret shares. Here, each party is going to calculate the bit decomposition of its individual secret share, and all parties are going to send their bit decompositions to the authenticated bit functionality to receive authenticated bits of their bits. Great. Now each party is going to hold kappa authenticated bits as the shares were originally in the field due to the kappa originally. As we have our authenticated bits, we need to prove that they are well-formed and indeed represent an appropriate threshold secret share. Our technique for this is fairly straightforward. We take two different size T subsets of parties, and with each subset, we calculate the interpolation of their respective authenticated bits. This gives us two authenticated polynomials, each of degree T-1 as we desire. We then check for equality of these polynomials by evaluating each at a random point, and by the Schwarzschild lemma, these evaluations being the same implies that these polynomials are the same, except with negligible probability. By the uniqueness of Lagrange interpolation, checking that the difference between these two evaluations is 0 tells us that we in fact have the same polynomial, and we have well-formed secret shares. Now that we have verified the polynomial shares, we can define our threshold authenticated bit to simply be the collection of authenticated bits from before. I will define the convert function to be the function that converts a T of n threshold authenticated bit into a T party authenticated bit by applying the interpolation procedure to the local authenticated bits. So what I just described is how we implement the setup phase of f-thresh. Here, which I encapsulate as an which I encapsulate here as a f-tabit functionality. Altogether, the parties will come together and request sampling threshold authenticated bits to receive their threshold key share. If you want to do additional computation, you can use these as inputs to FMPC, which I'll show you in just a second. With our threshold authenticated bits, we can construct the PyThresh protocol that realizes f-thresh. Our protocol allows the parties to produce an arbitrary authenticated threshold shared state during setup, and then allows the parties to use said setup without any additional communication during the evaluation stage. This achieves our efficiency goals and gives us the stated claim of threshold symmetric cryptosystems with low overhead. Pictorially, to mimic our definition of f-thresh, PyThresh is the simplest example. PyThresh in the simplest example is as follows. Every party is going to sample a random key everyone jointly samples a random key that is shared as threshold authenticated bits. And then parties that wish to encrypt a message can locally convert their threshold authenticated bits into plain T party authenticated bits to use as inputs to FMPC. Here I indicate in green the only difference between our evaluation stage and just using FMPC on its own. FMPC will then happily compute the desired encryption as it can check the validity of the authenticated bits. And this, and this local conversion is the only additional step. Quickly to touch on asymptotic efficiency of our scheme with our choice of protocols for the implementation. The cost to generate threshold authenticated bits is O of n times kappa times L for n parties, kappa the security parameter, and L for the number of threshold authenticated bits. These are in per party communication costs. There's 0 overhead at evaluation time as all of the conversion is local. And otherwise, the cost of evaluating Boolean circuit is exactly that of the underlying FMPC scheme. Here I show the asymptotics for the YWZ-20 multi-party garbling scheme. Concretely, you can see that our scheme has a small overhead overrunning the baseline full AES circuit without any threshold sharing. And we get the benefit at evaluation time of having pre-processing. In comparison to the folklore scheme, there is an order of magnitude difference in both execution time and communication. In conclusion, we give a scheme for threshold symmetric cryptosystems with effectively the same cost as the base MPC. Our protocol makes use of a higher order polynomial vector OLE correlation, and these can interoperate natively with existing protocols. There has been a lot of work recently on vector OLE-based zero knowledge and garbling in the two-party setting, and we hope that many of these techniques can be applied to multi-party garbling as well to increase the overall efficiency of our scheme. And with that, thank you.